The following presentation is largely based on the research paper RetroWrite, Statically Instrumenting COTS Binaries for Fuzzing and Sanitation. The rough outline of the presentation will cover a conceptual background of important concepts to know, exploring the problem context of the paper as well as existing techniques that address it, before exploring RetroWrite as another solution, as well as introducing internal workings of it. After that, we'll dive into a proof of concept of RetroWrite, a practical application of it, as well as a performance analysis of it, before our closing thoughts and summary of it. So, background. Memory safety. It's historically the root cause of most major security vulnerabilities and is especially common in low-level language systems. In fact, it represents 70% of all vulnerabilities in Microsoft code. These vulnerabilities are not only more ubiquitous, but are also commonly exploited with dangerous results. One such exploit was Heartbleed, which took advantage of a missing bounds check in OpenSSL, the most popular open-source cryptographic library in the world, to hijack heartbeat requests, or the periodic requests sent to servers in order to keep connections alive. In normal situations, an OpenSSL heartbeat request would carry simple data along with its length, which the server would then simply echo back. However, because of this missing bounds check, an arbitrary length could be specified, resulting in the server accessing and consequently returning private random memory, which included sensitive information like usernames, passwords, or certificates, which obviously resulted in a lot of devastating consequences for users. Another infamous example was Morse Worm, also known as the Great Worm due to its mass infection of all existing computers. Among other vulnerabilities, it exploited Unix's fingered daemon, which was an interface to report on the status of the current system and user. Through long input strings, Morse Worm would overflow the daemon's memory, overwriting the state of the stack, which in turn gave it the control it needed to execute malicious code and replicate itself. By its end, 10% of the world's computers would be infected, resulting in resource exhaustion that left systems barely functional. Due to the ease in which they can occur and the profound consequences associated with them, the prevention of software memory vulnerabilities has been a leading focus in security. To solve this problem, there are two general approaches. Firstly, you can attempt to enforce full runtime memory safety. In other words, the program is continuously checked while it runs to ensure it never reads from or writes to memory it shouldn't. However, like it sounds, this is expensive. Every memory access has to be checked, while each allocation has to be tracked. In fact, it's actually prohibitively expensive, which is why it's not as commonly used. The alternative is to audit software and catch bugs during testing. So instead of making every possible interaction with memory safe, we attempt to perform tests which give some confidence in backing that specific programs are functionally secure. Currently, the modern strategy to detect memory errors is largely built around the use of feedback-guided fuzzers and sanitizers. Fuzzers, as a general concept, form and run random, potentially malformed inputs while monitoring the runtime for unexpected behavior such as crashes, memory exhaustion, or infinite loops to list some. However, this is by itself a limited strategy. So instead, modern fuzzers use coverage guidance, where program traces of executing inputs are captured, saved, and later used to inform the generation of future test cases. The general idea of this is that overall code coverage will improve, resulting in deeper execution in more rarely triggered on-the-edge scenarios. Sanitizers, on the other hand, are general tools designed to detect various types of established bugs. Like fuzzers, they modify the target software, but the purpose differs. Fuzzers modify the program to generate and run test inputs, while sanitizers modify it to perform additional runtime checks, such as verifying memory accesses and other critical safety properties. In combination, fuzzers and sanitizers enable the systematic discovery of memory safety violations by repeatedly generating and executed guided test cases that trigger sanitizer-detected faults. Unfortunately, this strategy isn't universally applicable to all software, with the most notable exception being binaries. But why exactly is this form of software an exception? Well, fundamentally, feedback-guided fuzzers and sanitizers require information about the execution of test cases. To get this information, code is typically modified during the compilation to hook specific instrumentation, which, once embedded, enables the ability to detect internal particulars. For example, what area of code was executed, what memory was accessed, or has undefined behavior even occurred. However, once software exists in a post-compiled form, integrating the instrumentation required for such analysis becomes difficult. Indeed, a problem with analyzing binaries does exist. But how important of a problem is this? Well, unfortunately, the majority of software used in everyday systems is in fact closed-sourced, meaning this issue of evaluating binaries isn't a trivial problem either. Fortunately, however, this is an active area of research with known techniques. Broadly speaking, there are three categories of binary testing. The first is simple black box fuzzing, where the internal workings of a program are treated as an unknown black box. Randomly generated test cases are fed into the program, while it's monitored for externally visible behavior, namely crashes. In other words, we completely ignore the program's particulars, sidestepping the inherent difficulty in rewriting the binary. However, because this is a simple strategy, only shallow coverage is ever gained, making it largely ineffective as a testing technique. The second approach relies on dynamic binary translation, in which the binary is executed normally, but its running instructions are intercepted, and in our case, modified with instrumentation. One key advantage of this technique is its natural support for self-modifying programs, which intentionally alter or generate instructions at runtime, such as in dynamic or in-place code optimization scenarios. In addition, because it operates directly on runtime information rather than relying on complex analysis, it scales effectively to large and complex binaries, while keeping the instrumentation logic relatively lightweight. Dynamic binary translation systems also typically cache translated blocks, so that previously executed instructions can reuse existing translations, improving the performance along frequently executed hot paths. However, despite these caching mechanisms, the indirection introduced by translation and instrumentation can impose a substantial overhead, with slowdowns commonly ranging from 10 to 100 times. Even with this trade-off, however, the approach remains the current standard for binary fuzzing, due to its flexibility and broad applicability. The last major approach is static binary rewriting, which is very analogous to the modern approach of hooking instrumentation during compilation. However, because high-level structure and information are lost post-compilation, binary rewriting relies on complex static analysis. This static analysis, similar to what happens at the compiler level, can yield powerful benefits, like optimizing the memory and runtime overhead. However, as stated before, it is complex and error-prone. The central difficulty of static binary rewriting is reliably identifying and relocating all code and data references after instrumentation. In other words, once you modify a compiled binary, you must correctly adjust every address that points to moved code or data, which requires distinguishing pointer values from ordinary constants, recovering relocation information lost during compilation, and updating all control flow transfers. The problem becomes especially challenging when dealing with indirect jumps, dynamically computed addresses, position-independent code, and interleaved code and data. Because static analysis cannot perfectly determine which values are pointers or which bytes are executable code, rewriting can easily miss targets or misclassify data, leading to incorrectly or broken binaries. In summary, each of these three approaches to analyzing binaries comes with trade-offs. Black box testing requires no modification of the program, but provides no insight into internal behavior, limiting coverage and the ability to insert security instrumentation. Dynamic binary translation allows runtime instrumentation with full visibility, but the overhead is often prohibitive for large-scale fuzzing or production-style deployment. Static writing, in principle, could insert instrumentation offline with low runtime cost, but executing techniques rely heavily on static analyses that are imprecise, complex, and do not scale well. In short, no existing method combines scalability, precision, and low runtime overhead in a way that supports security-oriented binary testing. As a result, this challenge remains an active area of research. RetroWrite is one such solution. Through its own analysis and criteria, it concludes that the ideal solution for binary security analysis would be a static rewriter that can intelligently add the required instrumentation as if it were inserted at compile time. But, as mentioned previously, such instrumentation which would require analysis involving challenges that are known to be undecidable in the general case. And this is true. So, RetroWrite chooses to sacrifice generality for reliability in the common case. It does this by leveraging a specific static binary rewriting strategy and constraining the problem space to a particular subset of compatible binaries, which still represents a realistic and meaningful coverage area. So, what is this specific technique? Well, as identified by the authors of RetroWrite, static binary rewriting includes three fundamental strategies. One approach is recompilation, where a binary is first lifted into an intermediate representation and then recompiled into a new executable. By operating on this higher level representation, the rewriting process can reconstruct control flow, fix address references, and apply transformations or optimizations in a structured way. As such, the authors of RetroWrite concede that this is the most powerful static rewriting technique available. However, recompilation relies on accurately recovering information that is not explicitly stored in binary, such as function boundaries, calling conventions, stack layouts, and data types, something that's extremely challenging in principle. Another approach is trampolines. In binary rewriting, a trampoline is a small piece of code used to redirect execution safely. It works by first taking a few instructions from the start of the original function and moving them into the trampoline. The space left behind in the original function allows the tool to insert a jump to an interceptor function, which can perform custom operations like instrumentation or patching. After the interceptor finishes, it can jump back to the trampoline to execute the original instructions and continue with the rest of the function. This design allows new behavior to be inserted without completely rewriting or moving the original function. The main idea involved with trampolines is that you're replacing a section of the original code to make space for this jump to new code. So you're not modifying the program size of the offsets in a way that would break it. However, depending on how they are implemented, it can significantly increase code size and overhead due to the indirection involved. Finally, reassemblable assembly rewrites binaries by first disassembling them into assembly code enriched with symbolic labels and relocation entries, enabling a linker-like process to correctly resolve references when rebuilding the binary. Conceptually, the idea is to convert the program from a flat sequence of raw addresses into a form where all important locations, such as jump targets and data references, are expressed symbolically rather than as a fixed and brittle numeric value. This process, known as symbolization, replaces absolute addresses in the disassembled code with symbolic labels that the assembler can understand and later resolve. Once symbolization is complete, new instructions can be inserted without manually recalculating offsets, and the modified assembly can be safely reassembled into a working binary. By operating directly on a structured representation of the original code, this approach largely preserves the program's layout and control flow. Essentially, by removing the brittleness inherent to binaries with symbolic labels, we're able to move different parts of the code and insert new code while still being able to reference those previous areas, meaning that the overall program layout largely stays the same. However, a downside of this approach is that its correctness critically depends on accurate symbolization. If any value is misclassified, so for example, a scalar is mistaken for a reference or vice versa, the rebuilt binary no longer functions correctly. Now, RetroWrite actually adopts the reassembly-based approach because it best aligns with its core requirements for binary fuzzing, which is to 1, maximize throughput, and 2, ensure soundness, that is, preserving the original program's behavior while remaining scalable enough for real-world use. At first glance, however, this choice raises an obvious concern. If reassembly fundamentally depends on accurate symbolization, and symbolization is fragile, doesn't this undermine the soundness guarantee that they're looking for? And in general, it would. RetroWrite addresses this tension, however, by deliberately trading generality for reliability, as mentioned before. Specifically, it targets x86-64 position-independent code binaries, where references to code and global data are encoded using RIP relative addressing. This architectural constraint makes it significantly easier to distinguish true references from plain integer constants, as you can always tell what is a global data or reference to code if it uses the RIP register, for example, as well as calculates an offset from it. So you're therefore reducing ambiguity during symbolization and strengthening the correctness of the reassembled binary. RetroWrite begins by loading the relevant sections of the binary needed for rewriting, primarily the text and data sections. It will also extract helper metadata such as symbol tables and relocation entries. The tool then disassembles the binary using a linear sweep, where the text section is linearly processed top-down to extract instructions, and builds a best-ever control flow graph. Now, importantly, RetroWrite does not attempt heavyweight recovery of the control flow, which keeps analysis lightweight and allows it to scale to large binaries. The next step is the core component of RetroWrite, symbolization. Using relocation information gathered during preprocessing and the recovered control flow graph, the system identifies constants in both code and data that actually represent references to program locations. These raw addresses are replaced with assembler labels, converting absolute references into symbolic ones. By the end of this phase, RetroWrite produces reassemblable assembly code that can safely be modified and rebuilt, as address references are expressed symbolically rather than as fixed numbers. After this, once reassemblable assembly has been generated, RetroWrite applies instrumentation passes. These operate directly on the symbolic assembly and allow flexible transformations of the binary. And after inserting this instrumentation code, RetroWrite performs a series of optimizations to minimize overhead and preserve efficiency. It analyzes the newly added instructions to determine the register usage and side effects, and based on this analysis, selectively saves and restores only the necessary portions of program state. It also carefully allocates registers for the injected code to avoid unnecessary spills or conflicts. In summary, during this stage, RetroWrite reduces redundant work and keeps the transformed binary efficient. Finally, RetroWrite outputs the fully instrumented assembler file. Because all references are symbolic, the file can be assembled using a standard off-the-shelf assembler. This generic assembly would resolve labels and generate a working binary, completing the rewriting process. To demonstrate its practical potential for binary analysis, RetroWrite implements binary counterparts to ASON, or Address Sanitizer, and AFL, American Fuzzy Lop, two of the most widely used source-level instrumentation tools. These adaptations serve as a proof of concept, showing that source-level testing and security tools can be brought to binaries in a practically meaningful way using the RetroWrite framework. However, before diving into a performance analysis, it's important to understand certain details of how ASON and AFL work, along with how they were adapted using RetroWrite, as this represents a realistic and exemplary case of its application. To start, ASON is a tripwire-based technique for detecting memory corruption. It places protective red zones around memory allocations, which serve as tripwires for out-of-bound accesses. If a program reads from or writes to one of these red zones, the access is immediately flagged as illegal. To enable this, ASON instruments every memory access and relies on the concept of shadow memory, a separate, isolated region that mirrors the state of the program's memory. Each time the memory access occurs, ASON checks the corresponding entry in the shadow memory. If that region has been poisoned, or in other words, automatically marked as a red zone or otherwise invalid, the access is reported as an error. Red zones are automatically poisoned when memory is allocated and unpoisoned when it is safely usable. This dynamic management ensures that out-of-bounds and use-after-free errors are consistently and reliably detected. Now, you might be wondering how RetroWrite's adaptation of ASON can accomplish this without high-level information, such as variable names, types, or buffer bounds. And the truth is, it can't. And this is an enduring challenge of the framework as a solution. In principle, RetroWrite could attempt to recover enough information to create more fine-grained red zones, but doing so would require over-approximation, which could easily generate false positives and conflict with its emphasis on soundness. To work around this, RetroWrite makes some practical concessions. For example, instrumentation is applied at the stack frame level, rather than per variable, since variable scope and type information is unavailable. As a result, only overflows affecting the entire stack frame can be detected, not those targeting individual memory objects. Furthermore, global variables aren't red zoned, because symbolization alone cannot guarantee correct transformation of the data section layer. So, for example, in this case, we would have a for loop, as well as access to a global variable within that for loop. However, if we were to instrument this code, we can kind of see that the RBX and R15 registers would no longer, or at least the R15 register wouldn't point to the correct location of the end of the global buffer anymore, because that instrumentation, or because that red zone would go below the original global buffer. We'd have no idea of when it would end and when it would start anymore, which kind of explains the idea of why it's difficult to modify global variables with this instrumentation or with this relabeling. Now, on the other hand, as a fuzzer, AFL works by maintaining a bitmap in shared memory to track which control flow edges are executed. When the instrumented program runs, it updates the bitmap to reflect the edges it traverses. After execution, AFL examines the bitmap to determine whether the input triggered any new behavior, using this information as feedback to guide coverage-based fuzzing. Now, by default, AFL relies on QEMU, quick emulator, to instrument binaries at runtime. However, as discussed earlier, this introduces noticeable overhead and reduces throughput. However, unlike ASON, AFL primarily requires a recovered control flow graph, which RetroWrite implicitly generates during its symbolization process. In addition, AFL already supports instrumentation at the assembly level, making it straightforward to adapt under the RetroWrite framework. This demonstrates RetroWrite's modularity and its compatibility with assembler-based processes, highlighting how existing binary analysis tools can be instrumented with minimal modification, essentially demonstrating the opposite of ASON. In summary, we've seen a concrete example of how RetroWrite can adapt and extend existing software analysis techniques, providing the foundation to next evaluate its performance in practice. Now, performance analysis is guided by the following questions. Does RetroWrite scale to large binaries? Is there an improvement against state-of-the-art binary-only memory checkers in terms of runtime overhead and coverage? Is RetroWrite competitive against source-based memory corruption detectors? And how does coverage compare with AFL? RetroWrite demonstrates strong scalability and practical application by successfully demonstrating the ability to rewrite a diverse set of binaries, including real-world software and various security and performance benchmarks. Namely, it is able to successfully rewrite popular production tools like TCP dump and readelf, Lava M programs with synthetically injected vulnerabilities, common weakness enumeration test cases from the Juliet test suite, which contains code with curated security vulnerabilities, and complex compute-intensive applications from SP’20 2006. By succeeding across these various binaries, many substantially larger than used in prior work, RetroWrite shows that its rewriting approach is capable of operating on realistic, arbitrary C programs. Using the spec CPU 2006 C benchmarks, ASON RetroWrite was shown to have a general runtime 300% faster than Valgrind, which represents a state-of-the-art binary-only memory checker, and being only 65% slower than source-level ASON, with this latter difference being explainable by the loss in optimization opportunities for instrumentation moving from source to binary, such as the inability to remove checks if compilers can guarantee safety. You can no longer rely, for example, on intelligent register allocation, or no longer being able to hoist memory checks outside of loops. Moreover, when using the Juliet test suite, ASON RetroWrite was shown to have a true negative and false positive detection rate equal to both modern tools. Furthermore, regarding true negative memory error detection, ASON RetroWrite, and Valgrind had respective detection rates of 76%, 55%, and 30%. In general, ASON RetroWrite was not as performant as traditional ASON, but it represents a significant improvement of current binary-only memory checkers. Regarding the performance of AFL RetroWrite, a comparison was made against current alternatives. Performance was measured along two axes: executions per second and the number of unique bugs triggered. As shown, AFL RetroWrite had a throughput largely equal to that of AFL source code instrumentation at assembly level. Moreover, it was significantly more performant than QEMU, the current AFL tool for handling binary-only analysis. From the Mann-Whitney U-test, we also see that this improvement over QEMU is statistically significant, while any discrepancy between AFL RetroWrite and AFL source code instrumentation at assembly being within measurement noise. Furthermore, AFL RetroWrite shared the best results for unique bug detection, highlighting its superiority over higher throughput alternatives which used less effective coverage guidance, a fact that is most likely correlated with shallower coverage explaining higher execution rates. However, it is important to note that these results were based on single runs of only a small number of programs over a 24-hour period. Overall, RetroWrite represents a promising approach for binary analysis and instrumentation. It offers significant performance improvements over traditional binary-only tools like QEMU-based instrumentation or Valgrind, making it faster and more practical for real-world use. At the same time, RetroWrite relies on AFL's assembly time instrumentation, which has been reported to incur 10 to 100% higher overhead compared to equivalent compile time instrumentation. As a result, while RetroWrite narrows the gap, its performance still falls short of the efficiency achievable. Additionally, its reliance on structured x86-64 PIC binaries limits its generality, though PIC is becoming increasingly common, making the approach more broadly applicable.